Okay. So I hope you are still able to see my
Yeah.
cursor, right?
Yeah.
Yes. So welcome to week 7. So last week we could not cover the questions from week 6 also. So what we'll do is today we'll cover all the questions, assignment questions first, remaining ones from week 6 and then week 7, and then with the time that we are left with, we will look at a few more questions to get some practice in problem solving. Okay. So we had stopped at, I think it was question 4 that we stopped at, if I recall correctly.
4 or 5.
4 or 5. Ah, we had covered till 5, yes.
Yeah, 5 I remember.
So, so remaining questions from week 6. So I hope things are still visible and everything is fine.
Yeah, it's visible. It's fine.
Okay, so the question 6 says, which are true, which of the following uh, the options are as follows. LP always has a unique solution. Is this true?
No,
And why is that?
it may not have any solutions at all, right?
No,
It may be
if it has
unbounded.
solution, okay, yeah, correct. But let's say if even if it has solution, does it have to be unique?
It doesn't have to be unique. It can be a line
Yeah,
segment.
if two BFS are there, then convex
Yeah.
combination of BFS also a solution, right?
Yeah.
Let me see if still recording. Yeah. Okay. Cool. Feasible region of LP is always a convex set. So the feasible region of LP is always a convex set. What about this?
This is true, right?
Okay, so we'll just go with a standard form of LP. So we have meaning x C transpose X such that AX is B and X greater than equal to 0. So it is easy to see from these two cases, right? AX equals to B and X greater than 0, that's a convex set, right?
Yeah, it's a half places bounded by half planes, right?
Yeah, so this X greater than equal to 0 basically says one orthant, the positive orthant,
On
non-negative
orthant, yeah.
orthant. This is just a linear system of equations. So here you can, instead of X, what we can do is we can just put lambda x1 plus 1 minus lambda x2, and we see from the linearity that it will satisfy it, right?
Yeah.
Convexity definition. So
So that is an affine set, so you can anyway say it's convex, right?
yes, uh affine doesn't need to mean it's convex, right? Does it?
Yeah. Uh, does affine sets imply convexity? Yeah, because it includes the entire line, so that it includes a line segment also, right?
Oh, okay, yeah, sorry, my bad. Yeah, so okay, yeah, lambda 1 x1 plus lambda 2 x2. Only thing that I require is lambda 1 plus lambda 2 is 1. That's all. I don't require anything else.
Yeah.
Yeah, correct.
So
Yeah,
that is
sorry.
satisfied
Yeah,
then.
yeah, my
Yeah.
bad. Yeah. Okay. So there is one more. So B is true anyway. LP can have exactly two solutions. what about this?
No, but this is again false, right? Because it has two solutions. Any convex combination also be a solution, right?
Yeah, so x1 and x star solution. So this implies lambda x star plus 1 minus lambda x star x star star also a solution. Right. One more. One last option we need to check: feasible domain of LP cannot be a single point. Is this true?
It can be also true, right?
Correct. Yeah. So for just to
Yeah.
draw a
Yeah, it's
cartoon, for example, can have one constraint that is like this. Some other constraint that looks like this, and let's say this is the orthant I need to be in. So then the unique solution, I mean, just for simplicity, I'm saying it's the point here, right?
yeah, this is possible.
Yeah.
Right?
So I mean, I'm assuming here that if you the C will be orthogonal here. So when you move in this direction, you reach a minimum. So I'm assuming all those convenient things, but I'm just trying to say that even without that, the way I have defined my constraints, this is the only feasible point.
Yeah.
I mean, so I mean, yeah. So I take back my comment earlier. I don't need to worry about whether the C and C transpose X is aligned in certain way or not. Here, by definition, my feasible set is a singleton, right? This orange point.
Yeah, the feasible set is a proper polygonal region, right? Polyhedral region. So that's not an issue, right?
Yeah. So here it is just a singleton. So this is my
Yeah,
constraint
it's a
one.
singleton. Yeah.
Yeah. So here
Yeah.
this is my constraint one. This is my constraint 2, and this is my constraint 3, right? So
Yeah. Yeah.
so here what I have is C1 intersection C2 intersection C3 equals to my feasible region, right? LP feasible region, and then this is nothing but the orange point.
Yeah, by going by the definitions, there is nothing stopping it from being feasible. This thing, a
Singleton.
feasible region.
Yeah.
Yeah, a singleton or a
Yeah.
feasible region.
So that means this is wrong because I just now constructed a case. I mean, you can explicitly write down the equation for C1, C2, C3, but that's not really important. C3 is anyway easy to write here. The C1, C2 also you can just put x and minus x, y equals to x, y equals to minus
Yeah.
x.
Yeah.
So yeah, so D is also false. Okay, question 7. So we are looking at a LP. So we are looking at the primal and the dual. So I'll denote it by this bracket P and bracket D. So let's say the primal solution is X star, and let's say the dual solution is Y star. So then claim is X star equals to Y star. So is this true?
Yeah, this is true, right? By strong duality.
But is it always true? See, okay, so that is very, so it is very important. So here, I'm talking about the minimizer, not the cost value. So what you are saying,
Okay. This is the objective I'm telling. Okay. Ah,
okay, so
got it. Yeah.
by a strong duality, optimal values,
Optimal values are equal. Yeah, not the points.
okay. So this is what we
So
have
this
by
should
strong.
be false. So
Yeah,
this is false. This
yeah.
claim, right? Yeah, it's
But
false. Yeah.
recall, so I'll just write again primal and dual in the standard form. So dual for the primal in the standard form. So my primal will in the standard form will be minimum C transpose X such that AX equals to P and X greater than equal to 0, and dual will be maximum Y P transpose Y such that A transpose Y less than equal to C, right? So
Yeah.
here so what I'll do is I will denote this visible region by FP for primal, and I will denote the visible region for the dual as FD. Okay, so here FP and FT, they are different visible regions.
Yeah.
Okay, and they are moreover they are in different spaces. Right, so if let's say X belongs to FP, so this implies, so yeah, FP is basically some subset of what, so let's say X is in Rn, so FP will be some subset in Rn, right? And let's say Y belongs to FT, shall be some, so let's say there are M constraints, so let's say A is M cross N, right? So Y will be in this
Yeah.
subspace, FT will be in this some subset of Rn, right? Rm, sorry. Okay,
Yeah.
all right. So yeah, answer is
So it can never be the case that M is equal to N, right?
maybe some pathological case, possibly. I mean, it doesn't have to be.
Okay. It may be a coincidence,
Yeah,
right?
it might be a coincidence. Maybe you could just set up the system of equations such that you can get, even the M and N are different, but you can get the same point perhaps. Let's say, uh, I'm just thinking out loud. Maybe the minimum and maximum value, the primal and dual optimal values both are 0. In that case, I think I could get X star Y star to be 0. But I think I could set up a problem like this. Maybe that's a nice exercise. You can just try it out. I
Yeah.
think we
I
could do that.
just thought I came out of my mind suddenly.
Yeah. I think we could set up such that both X star Y star, I mean optimal values for both are 0, and which will yield that both the minimizers are also 0. I think that should be doable.
Okay. Yeah.
There are two sets. The next question, there are two sets. which are closed and they are disjoint. So then the claim is we can always find a hyperplane. Let's call it let's not give any note. I'll just write the equation for the hyperplane. Normal is A. So I can always find a hyperplane which separates the two sets. That is A transpose X less than equal to B for all X in S, and A transpose. So I'm not saying strict separation, I'm just saying a weak separation. So they could touch at some points. I mean this hyperplane. So is the claim true?
No, this is false, right? Because they need to be convex, right, for a claim to be made.
Okay,
Closed and
can you
convex.
think of any counter example?
Yeah, you just put a kidney bean shaped set, and in the notch you can put it circle so that it slides into that notch, and those two are closed and closed sets. Yeah, something along those lines. Yeah.
Right, so here like you said ST are closed, right, in R2, and ST are disjoint. Obviously this is not true.
So Deep, one question: where to find the proof of the separating hyperplane theorem? Is it there in Boyd?
They have for one case, I think general case they have put as an exercise.
Okay, in Boyd, right?
Yes, I think so. I think
Oh,
they have done a
oh,
slightly simpler case, and a slight the generalized version they have given some hints probably if I recall correctly. Maybe we can do that
okay,
next
okay.
time if you are if you have any doubts. Yeah, we can definitely.
Yeah, I think since you have said it that I'll just go through that. Let
Yeah.
me see. But the instructor didn't touch upon any proof, so that's why I was asking.
Yeah. Instructor did not cover the proof. Yes.
So a related question is: the separable this theorem is true for sets in Rn, or it can be generalized to more abstract sets?
Uh, I am not sure. Yeah, I don't know if.
Okay.
So when you say separate, so you are saying in any other metric space, any metric space in general. Is
Yeah,
that what you're saying?
yeah. Apart from Rn, any manifold, say.
Oh, mm, yeah. I mean, I in that case maybe instead of hyperplane you'll have to say something else, right? So just to maybe say one point, even other than
Yeah,
separating hyperplanes. So, for example, you might have seen the definition of convexity, which says,
yeah. I've seen that.
uh, actually, I don't even need to do this. I don't even need to go to functions. We'll just take sets. So we had some set and we took 2 points, right? And we took the line joining them. So, but is a
Yeah,
Euclidean space. If I didn't have the Euclidean space,
Yeah.
So I can't write this. I can't. This doesn't make any sense because, for example, this circle is a manifold, right? So if I am
Yeah.
taking 2 points on this circle, if I am joining
Yeah.
this line segment is not on the circle, right?
Yeah.
So actually, I'll have to go around
Yes. Yes.
the geodesic, right?
Yes. Yes.
So this thing will get changed to the geodesic
Geodesic. Yeah.
between xy
Yes. Sure.
on the manifold, right?
Yeah.
So these
So the
kind of changes
definitions.
will come
Yeah.
up here, but I don't know if this
Ah.
hyperplane equivalent thing, I'm not sure what does that turn out to be. I'm not experienced in any differential geometry, so I don't know. Maybe there are analogs
Ah.
of that, not linear, but maybe
Yeah.
something else.
Maybe. Yeah. Maybe there are analogs to that. Yeah.
Okay, so yeah, that was a slight digression. Let's come back to the questions. So yeah, what we need is actually closure is not enough. We need convexity, right? So that is the important property we need. Closure alone is not enough. Okay. Then we have feasible region F, which is given by a. Okay. So basically, it's an LP. In the standard form. Okay, and A is, we have the numerical values given. A is a 2x3 matrix. So there are two constraints, and this is the linear system we are given. So the question is, which of the following is an extreme point? So I'll give some options and just try to guess along with the reasoning for why I think this could be an extreme point.
So I thought of doing it by finding the basic feasible set by like the B transpose B inverse B thing, but I
Yeah,
did not
so
get it right for some reason. I think.
yeah, so you're on the right track. So the idea is that extreme points are that's what we proved, right? They are the basic feasible solution
Yeah.
of the system Ax equals to B. So basically in this matrix A, what are the linearly independent columns?
You take any of those. First and two will suffice. First and second column if you take.
First and second, right? Okay. A has rank 2. You are right.
Yeah, it has rank two, so any two will do.
Right. So that means that C is not possible, right?
C is not possible. Yeah.
Yeah. Here A has rank 2. This implies not C. Okay. So what else can we do now? So there are three options now. How do we eliminate?
That's what I was stuck there. Uh,
See, we have to always check feasibility. So what do you mean by feasibility?
all the x's should be greater than zero.
Yeah, so that at least that basic check is satisfied here, but there's
Yeah,
one more check that we have to
yeah,
do,
that is
right? So we noticed that x greater than 0 for a, b and d, right? What about ax equals to b? So let's check for a. So the first option is 1 2 0. So the matrix that we are given is, just to recall, 2 3 1 1 1 1, and the option that we are checking right now is 1 2 0. This is a potential, this is a candidate. We are checking for feasibility, and b is given to be 8 and 3. Is this possible?
yeah, that is not yeah, that is possible. Yeah.
So this is fine, right? Because it's just 2 plus 6 plus 0. How about b? So again the system remains the same. All that changes is our candidate, which is 0, 1.5, 0.5, and we have to check whether this is equal to 8 and 3 or not. So 2 times
No,
0 is
this
2.
doesn't work.
So this doesn't work,
This
right?
doesn't
This
work.
doesn't work. So clearly b is not possible.
This is the idea. Yeah, I did not do that. Yeah, got it.
So feasibility is always a necessity, right? That's it's not a sufficient, it's
Yeah,
a
that is
necessity.
necessity.
Yeah.
It's necessity. Yeah.
So we'll do one more check, because we have just eliminated B and C for now. Uh, A and D are the ones that have to be checked. Yeah, sorry, D not C. C is anyway not a feasible solution. System remains the same. The candidate is 0 1 3, and again
This
we
is
have to
also
check.
not possible.
Yeah, so here you have 2 times 0, 3 times 1, and 1 times 3. So clearly 6 not equals to 8.
Yeah, that is
And
impossible.
obviously when this is not, 4 is not equal to 3. So right, so this is not equal to, so a belongs to the feasible set, right?
Yeah. Here
So
we can just do by elimination, but if there are two potential candidates, we have to check further, right?
no, but does this still answer solve the problem, or do we have to check something else?
Uh, yeah, but we need to check further, right?
What we have to check?
That this is actually a basic feasible solution.
Yeah, so if the corresponding non-zero columns, I mean the corresponding columns corresponding to non-zero entries of x, that's what I meant. So here this
Yes.
is our candidate, right? So we want to see whether
Yes.
this and this column, this and this column, are they linearly independent?
Yes.
Are they though?
They are linearly independent, right?
Yes. So yeah, maybe let me rephrase this sentence. So what I want to write, we have to check if the columns of A corresponding to non-zero entries of x equals to 1 to 0 are linearly independent. Indeed they are. So what does this say? This is a BFS.
Yes. Yeah.
Okay, so yeah, just merely feasibility doesn't mean that it is uh, Yeah, merely being feasible doesn't mean that it has to be a basic feasible solution.
Yeah, yeah.
So far, so good. Just to
Yeah,
maybe to,
so
yeah,
this is question two more are left, right? One, two, no, three are
three
left.
more, yeah.
Three more are left.
Okay. So let's say the primal problem is infeasible. Then which of the following are true? For the dual. So the options are dual has unbounded optimal value. Dual has finite optimal value. And dual is infeasible. So which of the following may be true? Yeah, I'll be a bit careful. Which of the following may be true? So what can we say?
So right off the bat, we could say that C is infeasible. That is definitely true.
Yeah, sorry, I meant to write infeasible, not feasible. Yeah, that's one possibility. Correct.
That's one possibility.
Can it have finite value? Finite optimal value?
Uh, yeah, no, that is also not possible by strong duality, right?
Yeah. So that's not possible. I mean, this is basically the
And
theorem that we derived in the class. It's exactly the same.
yeah, yeah,
Another possibility is that how can dual be infeasible? One
yeah.
more
Dual
way is
can be
that
infeasible by
unbounded, right?
it has unbounded. It's unbounded. Yeah.
Right. So this is just the result we have seen in the class. Okay. Now a slightly numerical problem. So we are given an LP in the standard form. Well, it's not a standard form actually. It's not. Uh, so the thing is, we are given the solution. So x1 star x2 star is 0 comma 4. So this is the primal, and the dual is minimize y1 y2 4y1 plus 2y2 2y1 plus y2 greater than equal to 1 y1 minus y2 greater than equal to 2 y1 greater than equal to 0 y2 greater than equal to 0. So the question is, which of these can potentially be the optimal solutions of the dual problem? So even without stating the options, what do we need to check for this, for to answer this question?
We have to check first the feasibility, right, of the dual.
Yeah. So for example, if I give these candidates, so feasibility is a necessary criterion that has to be satisfied.
So first, for problems of this kind, first we can eliminate by feasibility, right?
Yeah, if maybe
Eliminate
there are
options,
some
right?
infeasible points, so let's just eliminate them right away. So are there any such points that we see? At least all of them are non-negative, so that one check is obvious,
Yeah.
which doesn't reveal anything.
Yeah, but I think B is not possible, right?
B is not possible because of this constraint, right?
Second constant, correct.
Yeah, so let me write that. So B is not feasible as y1 minus y2 equals to 0 is not greater than 2. Okay, what else can we say?
Hmm. From there, I'm not sure how to proceed for this. No.
So what other thing do we know? What is the optimal value here for primal?
Optimal value, you just plug those values here, so that gives 8, right?
Yeah, the optimal value is 8. So can we, based on that, can we say something about the optimal value of the dual?
Yeah, it should also be 8, right?
Yes. So by strong duality, uh, primal optimal value equals to 8 equals to 4y1 star plus 2y2 star, right?
Yeah.
So is there any point that satisfies that?
Hmm. Have to check. Just
So C
scroll
does,
up a little bit.
yeah. So for example,
Uh,
C,
so
y1 being 1 and y2 being,
one,
that
one,
doesn't work,
one,
right?
three, right? That doesn't work. Yeah, true. Doesn't work.
So 1 3,
Even B doesn't work. Then
just a second. So B is anyway removed, right? B is removed from the,
yeah,
it's
B is
not
removed.
even a feasible point.
B is removed. Yeah, B
Right?
is
So even
removed.
C is not, because so y1 y2 equals to 1 3.
Yeah, only D is the option left.
Yeah, so 4 into 1 plus 2 into 3, 6 plus 4 10, which is not 8. Okay, so C also not possible. Okay, so what are our options?
A doesn't satisfy. That
uh,
it is equal to A.
A does satisfy.
Yeah, A satisfies. A does satisfy. Yeah, A does satisfy, and D also satisfies.
So be careful. So may satisfy that, but is A even feasible? 0 and 0 comma 4. What about this?
Okay.
Right?
Zero. And that is okay, right? -4 is okay. Yeah.
Right.
That is
So
not.
the
I
problem
just
with
missed that.
A
Yeah.
is
But
y1 y2 is 0 4, implies y1 minus y2 is minus 4, which is not greater than 2. Therefore, it is not even feasible.
we should have eliminated it beforehand
Yeah.
only.
Yes.
Yeah,
What
missed
about
that.
D? D is y1 y2 is 0, uh, 2 comma 0. Feasible. So let's just quickly check that. So we are
Yeah,
checking for our D last option, 2 comma 0. So when we put 2 comma 0 in the
yeah, that
optimal value,
satisfies.
which is indeed 8, fine. uh, 2 2s are 4 plus 0 greater than 1, that's true. 2 minus 0 is greater than equal to 2, that's fine. Both are non-negative, that's fine. Feasible. And uh, 4y1 plus 2y2 is 8. So therefore D is a candidate solution, right?
Uh, yeah.
Oh, last question from this. Again, we are given some LP. It's not in a standard form, just like the previous problem, but that's okay. Minus x1 minus x2 is then equal to minus 4. x1 plus x2 less than equal to 2. x1 greater than equal to 0. x2 greater than equal to 0. So yeah, so the question is, dual of this LP is feasible. So this is a claim. Is this true or false? Is the set here that satisfies this constraint, is it non-empty? We need to first look at that.
Yeah, that's what I was thinking, whether it's empty or not. That's the.
So can we rewrite this as something else?
Yeah, greater than equal to.
So how does this region look?
This is empty, right?
No, so these are
This
two
is greater
different
than equal
lines.
to.
Is it really empty?
Its intersection.
So first
X1 greater than
thing to
4.
notice, we are here.
Yeah, orthant, yeah.
Yeah, the next thing is x plus y is equal to 2. We'll just draw that. So let me take color.
Yeah, these are parallel lines, they are disjoint.
So it is this region, right? And similarly, like you said, the other case. So, but what is the, yeah, so what do we do now in this case?
Yeah, so basically we have as a solution left only a what we have no points, that is empty, right? The feasible region. So this LP does not admit any solution, right?
Yeah, so here the feasible solution is empty. I'm just checking if they have any typos or not, because they seem to be getting a different answer.
Yeah, true. Minus x1 minus x2 is equal to 4.
Okay, let me check if we are still recording. Okay, yeah, good. Recording is going on. Yeah, this is a. I feel like there is some typo here.
There should be some typo. It does not admit any solution, right?
Yeah, the physical region is empty.
Yeah, maybe this is true by being vacuously true. It may be possible like that. I don't know.
No, no, no. No. It's feasibility requires it to be non-empty. So it's
Okay,
not
okay,
that statement doesn't apply here.
okay.
So optimal value should be 16, I think, from what they've written. I think there is some problem with the signs, but anyway, not that important. So leave it. Let's just leave this. I think there is some typo.
They will probably clarify it later, right?
Yeah, I think we need to, or I mean, as long as the idea is clear, this specific question is not
Yeah, yeah.
that.
It's yeah. That's not an important thing. But the solution means I can 110 as acha. Okay, they are giving 110 as a feasible point. I don't know how.
Yeah.
Yeah, there is some issue with this question. Yeah.
Okay. So week 7 questions. Let's look at that.
So Deep, what are the applications of Farkash lemma? Means is it very applicable in problems?
Not that I'm aware of. You might see some alternate proofs. That's where I've seen it being used. Other than that, I
Okay,
personally haven't seen applications of it.
okay.
So we'll just dive into the questions and then solve a few more based on whatever time we are
Yeah,
left with.
yeah. It's better to. Yeah, yeah.
Okay, so again we are having an LP problem. So we looked at some max flow problems in the lecture. I mean, we didn't solve anything, we just stated as an application that we could state some problems as these LPs. So here, what we
But
are,
till now we haven't solved any LP till now, right? Formally.
yeah, we haven't solved any till now, yes, because the thing is, it is a constant optimization problem, and we haven't yet derived what are the necessary and sufficient conditions to for an optimal point to satisfy to be called minimizer. So once
Okay,
we
we
do
do
that,
not
then
have the
we can
necessary tools
immediately,
as of now.
sorry.
Okay. We do not have the necessary tools as of now, right? This
Yeah,
is what you are saying, right?
right now we are just
Okay.
stopping at checking feasibility, and consequently, I mean, we're just saying that okay, there are different ways of stating the problem, but we haven't actually started solving the problem.
Okay. Okay.
So the question is that there is a LP. What we are doing is we have to maximize this 3x1 plus 2x3 is subject to these constraints, and what we are given is that 0 comma 1.5 comma 4.5 is the optimal solution of this primal. The dual is given by the following. Okay, and let's say y1 star, y2 star, and y3 star are the optimal. This is the optimal solution. Of the dual. So, question is, what are these values? So, how do we do this?
So I proceeded by using complementary slackness.
Uh,
I have found lambda 1, lambda 2, lambda 3 through that proof. I don't know.
See, I mean, yeah, it's not the only way to do it, but so I'll just suggest one way that uses the information that we are given here. I think you indirectly done the same, but let's start like this. So,
Okay.
what does this mean? What does this information tell us about the optimal solution of P? So you said something about complementary slackness. So I'm guessing you then utilize this information about this 0.0, 1.5, 4.5 being
Yeah.
optimal, right?
Yes.
So how did you go about that?
So I did it through writing out the complementary equations, complementary slackness equations, which hold that is lambda transpose ax minus b at the optimal point, and A transpose lambda minus C transpose x is equal to 0, both of these equations. And then found out a solution for lambda 1, lambda 2, and lambda 3 by solving those simultaneously. I plugged in the solutions for those in those equations for H star.
Okay, right. So I'll just suggest a slightly shorter way to do it. So
Yeah,
I
this
the
is a
thing
bit
is,
long.
yeah. So the thing is, I want you to use this information. How do we do that? In general, you are right. I will set up the complementary slackness equation and I'll solve that. Here it's a bit simpler. So we can take the help of this for this fact, whatever the optimal solution of P is given to us. So okay, so again we will focus on the constraints, okay? So these, the ones that I'm highlighting with the red pointer, is are my constraints, right? And this is my
Yeah,
optimal solution, 0, 1.5, 4.5. Clearly the first constraint is satisfied with equality, yes?
yeah.
And what can I say?
0, 1.5. Yeah, it's equality.
Yeah, and how about this? Sorry, second one.
Yeah.
2x1 minus x2 plus x3. So this minus 1.5 plus 4.5. So that's also with satisfied
That is
equality,
equal.
right?
That is also equality. Okay.
But what about this one? 3x1 plus x2 minus x3. That's a strict inequality, right? Because
It's check
1.5 minus
inequality. Yeah,
4.5. Not. So previously it
yeah,
was
yeah,
minus x2 plus x3. Now it is x2 minus x3.
yeah.
So
So yeah, got it. You're getting the idea. Yeah, tell me.
yeah, so the fact that 0, 1.5, 4.5 is optimal solution of primal, the constraint constraint 3, what is it, 3x1 plus x2 minus x3 is inactive.
Yeah,
Okay, so then I know automatically that y3 is 0.
yeah,
It's fine.
yeah.
So okay, so sorry, y3 star, not any y3, y3 star.
Yeah, voice is stuck. That's the optimal. Yeah.
See, so this basically I use the same complementary cycles only. Only thing is I just utilize the information about the optimal solution being available. What you did, we are doing the same thing, only difference is that here we are explicitly using the fact that we are given this optimal value for primal, or optimal solution for primal.
Yeah, the full machinery is not required. You can just eliminate options based. Yeah.
Yeah, so what else can we say? So can you just help me out the way you solved it? Can you just repeat some of those steps? I mean, sorry. Can you just tell
Yeah,
me some of the
it's
steps? Yeah.
yeah. I just I just wrote down the complementary slackness equations.
Right. So can you? So okay.
Yeah, this lump
So what you're saying is y star transpose.
transpose
Okay, but then I'll
A
have to
star
write.
minus B.
Yeah. So I'll have to then define this is 0
Yeah, this is
and
0
a
and
star y star minus c x star is 0.
yeah, yeah.
Okay. What is a?
A is 1, 1, 1. I'm telling row wise.
Yes, 1 1 1 2 minus 1 1 3
2 minus
1.
1 and 3, 1 minus.
Similarly, b is 6 3 3
Yeah.
and
And C
c
is
is
302.
302. Right.
302.
Right. So yeah, I think maybe I was wrong. So maybe I don't think we can infer anything beyond y 3 star equals to 0. I think we'll have to use. I was under the impression I could reduce further, but I guess not.
But that doesn't fit a kind of first question. I thought a first question would be a bit simple. But anyways, yeah.
Yeah. Right. So yeah, we'll have to go this route. So I think this should. Well, I just know the final answer. I think I'll skip the algebra here because once we have done this, it's just adding and subtracting a few variables. So I think this is the solution.
Uh, yeah, Y star 1. Yeah, there's the solution.
110, right?
110. 110. Means if you write down the equations and put in the values for x star, it simplifies quite a bit. Then it's simple.
I see. Okay. Yeah, I think one. I mean, y3s are anyway 0, so maybe it will become further simplified to solve it.
Yeah.
Uh, what else I was supposed to say? Yeah. I mean, we can always do a sanity check. So this y star is 110. When we plug it here 110, we are getting the optimal value to be 9, 6 plus 3. Here
6
in the
plus 3, yeah.
primal case, we have 1.0, 1.5 and 4.5. If I plug it here, I am
Yeah.
getting 0 plus 2 times 4.5, it's
9,
9.
9.
So just a
Yeah,
sanity check.
9. Yeah.
So yeah, we don't seem to have made any mistakes in solving this. Okay.
Yeah.
So shortest path problem with m nodes and n edges. Okay, so the LP can be then written as so just I'll just briefly recap. So the point is that when you have a, let's say this is your source and this is your target. I hope you are able to see on my screen still.
Yeah.
Yeah, okay. So, I could end up going in all sorts of ways. I could go directly, could end up going there and then going here, or I could just go straight. I mean, there could be so many different ways of going.
Just one small question here.
Yes,
Here they give it all in the sort of directed graph. So is
yes.
it possible to give undirected formulations also of these problems?
Uh, I think you can just add an extra arrow. But I mean, in case of shortest path, it's assumed that you want to go from one place to the other. So at least in
Okay,
this
okay,
case,
okay.
doesn't make sense to have.
Yeah, doesn't make sense. Yeah.
Maybe you could have
But
two ways.
no,
Not
but
sure.
in the flow problem,
Right.
the instructor gave us example wherein he mentioned bidirectional edge. So that's why
Yeah, yeah. So
I was asking.
this is not a problem. This is a shortest path problem. So
Yeah, that's
here the
problem. Yeah,
capacity is infinite, but we are going from source to target.
yeah, that is the objective. Yeah,
Yeah.
yeah.
So
Got it.
the rationale behind formulating the problem like this is that uh, what I really, so each of these edges, they have some costs associated. So what I'm saying is,
Yeah, they have some cost.
okay, so actually what we really want to do is, if xij, so I, let's say I pick some path along this. So let's say I went like this, then I went like this, then I went straight. Or maybe alternatively I could have uh, gone like this, could have gone like this and gone like this, right? I mean, so many possibilities.
Yeah,
So in general, what I am really interested in is, let's say I went along the blue path. Okay, I hope you can see my cursor, my pointer.
yeah, yeah.
So here I'm basically adding the cost of traveling along these edges, right? So when
Yeah.
I compute my total cost, I assign xij to be 1 only to these edges wherever I am
Yes,
traveling.
yes, yes,
Rest are 0.
yes, yes,
Okay.
yes, yes.
So that's what I,
So basically, if that edge belongs to the path, then only we set it to one, right? As an
yeah,
indicator variable,
yeah,
right?
just an indicator variable. Okay.
Yeah.
So, I mean, this is actually what one would say convex relaxation. That's not so important. It just makes it a
Yeah,
bit
that is
easier to solve. Okay.
okay. This is a convex relaxation, right?
Yeah.
Yeah.
So this is, so yeah, this is the way, we would formulate it. So we are just trying to write that. So x is basically you can think of it as an indicator of going along which path. That's all.
Mm-hmm.
Okay. So A is in M cross N. So the question is, which of the following is true? Is true about the matrix A? Every row of A has exactly 1 plus 1 and 1 minus 1, and the rest as zeros. Or same thing, but I can say every column instead of row. So every column has exactly 1 plus 1 and 1 minus 1 and rest as 0. So any thoughts on this?
Yeah, so B will be true, right?
B will be true, okay, but why is that so?
Because if I look into a particular column, okay, so that shows the nodes that are incident on that edge, right? Because here the uh, yeah, so that means that edge is coming out from one node and going out from the another node, going inside another nodes, right?
Right.
So that means one will have a plus one and one will have a minus one, right? Corresponding to these two cases.
Uh, okay, but so there is something else that needs to be explained along with. So what I think should be added is, so let's say I'm here. Okay, yellow is probably not a good color. I'll switch to blue. Can still see it, right? I hope there's not much difficulty in seeing the blue pointer.
Yeah, it's okay.
Okay, yeah. So let's say I was at source here and then I went to some point here, the node next to it. Now from here, let's say I decide to go to, let's say, either here, so I from here to here, or maybe there was a direct path which I didn't draw it here, but let's say there's a direct path going from here to here. So from this node, the second node, if I decide to go
Yeah.
along this path, it's not
Hmm.
like some fraction of whatever was here gets to travel along this route and the rest of it gets to travel along other routes. No, if I pick a route, the
Yeah,
entire unit travels along that route.
yeah.
Okay.
So for the shortest path problem, we just choose the shortest weight and distribute everything entire weight
Yeah.
on that path only, right?
Yes. So yeah, correct. That's very important. So that is why we can say
Yeah, that's
about the
important.
explanation that you gave. That's why it works. Okay.
Yeah, yeah. Implicitly, that is important. Yeah.
So I'll just let me quickly write it down. So yeah, you are right. P is correct. And so Xij from node I to J. That's all. So therefore in A, 1 plus 1 and 1 minus 1 in every column. Rest are zeros. Okay. Uh, for the primal, and the next question is primal and dual of LP. If some point satisfies complementary slackness, then it is the optimal solution. So is this true or false?
Yeah, I had got it wrong. I marked it as true, but it came out as false.
Right. So see, the point is again the same, which is that feasibility always has to be checked. So
That is the catch.
yeah, feasibility is also required. Okay.
Hmm. means they must satisfy they must be in the feasible sets of the primal and the dual, plus they should satisfy the complementary slackness conditions, right?
Yeah, so the thing is that slackness condition could be satisfied by any some other combination also, right? What we want is
Yeah, true,
want
true.
a combination that also belongs to the feasible set.
Yeah, true, true. Yeah,
By itself, when you write that complementary condition, that does not impose any uh, constraint that okay, you have to be in the primal feasible region or the dual feasible region, right?
yeah. Yes, yes, yes.
All that we are trying to capture using complementary slackness, okay, fine. If one of them happens to be constraint happens to be inactive, then the corresponding variable in the other the dual optimization problem happens to be zero. So this
Yeah.
is something we need to be careful about. So visibility is always to be checked.
Yeah. Okay.
So the next question is where again we are still in the realm of LPs. So you have the system of equation Ax equals to B, and A is given to be this matrix and B is given to be this vector. Uh, the claim is that there exists some y such that y transpose A is 0, it's a vector, and y transpose B is not 0. So is this true or false?
I was not sure how to proceed with this. I tried using Farkas lemma, but somehow I couldn't get the hang of it. How to proceed with this? Hmm.
You can just appeal back to linear algebra, something just some first principles approach maybe. Okay, so what is the rank of A?
Rank of is
Can you just check
two
quickly the
fives.
determinant what it is?
Oh my god, that is horrible. Okay, let's do it. It's at 6. It's 14. I think it's 2 minutes. It's 8.
It's not invertible.
Race, yeah, yeah.
So can you find some
Singular.
dependence?
Two, 3. If we sum up first column and third column, that gives 3, 12, and
Sum up
6.
the first and third column, is it?
I'm thinking
Yeah, you're right.
to, yeah, yeah, yeah.
So this is 2 times A2, right? So A2 is
Yeah, that's
so
what,
rank.
yeah, I was thinking right.
Yeah, so rank
Yeah.
is 2. Is there any other dependency that we are missing out on?
Mm. No, no, I don't think so.
Okay. So based on this, maybe you can think of something.
Okay. Y transpose A is equal to 0 and Y transpose B not equal to 0.
So actually, I would suggest. So I mean, you're somewhat on the right track. So what I would suggest here is, it's instead of AY equals 0, we are looking at A transpose Y equals to 0, right? So what we are
Yeah,
really
means the row
looking,
space of A.
what we are really looking is here, not in the column space.
Yeah, the row space of A. So, okay.
Okay, so maybe let me just do this. So you can add this up,
3.
and you can
Yeah,
add this
5,
to
6,
minus
7,
4
8.
times of this.
Yeah, right. So minus 4, 1, 1, right?
Yeah.
So Y transpose is.
So A transpose Y will be 0,
Yeah.
and P transpose Y will be simply minus 24 plus 8 minus 16. Okay.
Yeah.
So we have an LP. So we
But
formulate.
Deep, I
Yeah.
was
Yeah.
Deep. Just a minute. I was a little bit unsure. Means why these kind of questions are, because this is does not pertain to directly the material taught. It's just a general question. That's why I was thinking whether we have to apply Farkas lemma or something of that sort.
Uh,
Huh.
I mean, I think you are right. I mean, there is some equivalent form that I vaguely recall he has taught.
Yeah,
Let
that's
me
what I
just
was thinking.
let me
It's
just check. There is a x. Okay. The thing is, although here we are given the A and the B, but for the Farkas lemma, we'd also need the C from the LP.
yeah, exactly. Need the
That's
C.
what I can infer from my notes, but we don't have that. So
I was trying to put C as 0 and trying to come up with something, but not successful.
yeah, maybe the question should have had a bit more information to be able to use forecast lemma.
Oh, okay.
So okay, so in question 5, what's going on is we have an LP, and we wrote down the primal and dual, but uh, and we are given that X star is the optimal solution for P for the primal. So question is, so this is some okay, yeah, so let me clarify this. So let's say someone is coming, so it's a difficult problem. This LP is a very difficult problem. You are not able to solve it. Someone comes along and claims this. Comes along to help you out by claiming that X is the optimal solution. So how to check whether their claim is correct or not? So any thoughts? Why? What all things
Yeah,
we need to check?
this is just from the definition of primal and dual problems, right?
Okay, so
You
what do you
check
need to check?
whether, first need to check feasibility.
Okay, so check if X star is primal feasible. You are right. Then anything else?
Yeah, the complementary slackness equations.
Can you elaborate a bit? What do you mean? So check feasibility and do something, right? You said.
Hello, Deep.
Yeah.
Yeah, there was a phone call, that's why.
Okay. Yeah. So I was just asking. You were saying that apart from feasibility, we need to do something else, right? So what you are saying is correct. So what I need to do is apart from checking the feasibility of X star, I need to see that this X star and there is some dual feasible point Y such that the complementary slackness holds.
Yeah.
Okay. So this is true. I mean, maybe I should. This is not enough. Uh, how about this possibility? So what I do is I check that X star is primal feasible and find any point Y such that complementary slackness holds. This is also fine, right?
Just give me a second. Check if X star is primal feasible and find any point Y such that complementary slackness
Yeah.
holds. But then Y star has to be dual feasible, right?
Yeah, exactly. So the whole point is not just to satisfy complementary slackness, it still has to satisfy the feasibility criterion. Okay? So
Yeah.
so these follow from complementary slackness theorem.
Okay. You just finished this question. I have a small question. I'll just ask you
Yeah,
once.
sure.
So, this is the question that I just came into my mind because the prof was alluding to it briefly.
Hmm.
He was telling that lambda can be interpreted as Lagrange multipliers.
Yeah.
So that way we can unify some of those business of duality and Lagrangian theory.
Yeah.
So it will come in the subsequent
Yes.
lessons, right?
Yeah. So he will
Okay.
the moment he for sets up give look starts talking about the constraint optimization. Both equality he briefly talked about, but for in general any function, not just convex,
Uh-huh.
any function, if I have equality as well as not inequality constraint, so how to find the optimal point there? That's when you'll see all these things come together.
Okay. Fine.
Okay. So on the question 6 says that LP is such that, so I'm given some linear program such that both primal and dual are feasible. So the feasible sets are non-empty. Then do P and D, the primal and dual, have finite optimal value?
This should be true, right?
Yeah, and why is that?
LP is such that primal and feasible are feasible. Then finally, it's not dual format optimal values. Yeah, that should be by strong duality. Yeah, that's right.
So by the way, note that in general this doesn't have to be true. It's only because it's a LP problem. It's a convex problem. So you'll soon see, I mean not right now, but you'll later on see why this is true. Okay. So if I were to give any arbitrary function, then this doesn't have to have the same have to have finite optimal value. I mean finite is okay, but doesn't have to be the same.
Okay, okay, but they still can be the optimal values, right?
Yeah. So here, okay, I think they are just asking have finite. Okay, they're not asking for same. Yeah, I think I read question incorrectly. But yeah,
Yeah,
finite
and
is fine, but they need not be same.
in case of general optimization problems,
Yeah,
right?
yeah.
Okay. Oh, then there will be a duality gap, right?
Yeah.
Got it.
Okay. So for an LP, the next question says for an LP, if the primal is unbounded, then the dual is also unbounded. So is this true or false?
This should be false, right?
Yeah, you are right. It should be false. But what should be the reasoning for this?
Mm,
So what we can say when P is unbounded, it just tells us that dual is infeasible.
yes, yes, yes. But unboundedness is
Yeah. Right, it just follows from weak duality.
yeah, it's not good.
So it's like saying P star greater than equal to D star where this is the optimal value for my primal and this is optimal value for my dual. This is unbounded and this is just infeasible. That's all we can't say that D star is upper bounded by P star.
Yeah, yeah,
It is a minimization problem.
yeah, yeah,
So this doesn't make sense unbounded. Okay.
yeah. Yeah, just like you cannot say an infinity is less than equal less than infinity like that, right?
Uh, yeah, I mean maybe you could put it like that. Yeah.
Yeah.
So the next question says that again we are in the realm of linear programs, so we will continue to look at different situations, but still they are LPs. So this is my primal, and I am told that the optimal solution is 0 comma 3. Then the question is what is the optimal solution for the dual? So the options are 1.8 comma 0, 0 comma 3, 1 comma 4 by 3, and 0 comma 0. So how to go about this?
Yeah, means this problem also looks the same as problem one. There is no such difference between essential difference
Yeah,
between
you're
this.
right. Yes, but the thing is here I have not given the dual.
Yeah. You are not given the dual.
So here
Correct.
what you suggested that actually makes a lot. I mean, that seems to be the only way to solve here.
Yeah, because they have given the hint, right?
Yeah, so use strong duality and complementary slackness because the dual is not so either. So right now we have not uh, gotten used to formulating the dual for any given primal. So we will just use this
Yeah,
condition that we know, which is the complementary slackness.
yeah. But when you say that we have not been given the formulations to formulate a dual problem, but he had already told how to formulate a dual, right, in the class.
So in general, yes, but so if I give this LP, how will you formulate that?
Yeah, this is not in the standard form, right?
Yes. So you can do it.
Yeah,
You are right. You can do it, but
yeah. Then you will have to, yeah. Then you have to put it. You have to put slack variables and all those things. You have to do it
yeah. So what
accordingly.
you'll have to do is you have to first convert. Uh, where's the pointer? Yeah.
Yeah,
So you'll
put
have to
two
first.
slack variables, right?
Yeah, you'll have to first convert this into a standard form,
Yeah,
right? So first of all is a max one. So you maximization problem. So you have to convert to a minimization problem. Then you, like you
yeah.
said, add slack variables, convert it into
Hmm.
the standard form. For that, you know
Yeah,
the dual form. From there, again, you have to
yeah.
massage the terms so that ultimately you get only the
Yes.
corresponding terms, and that will be the dual.
A- And maximizing conversion to minimizing is not very easy, right? You put a minus in front and then you minimize the objective,
Yeah.
right?
So
You put
if
minus two and
yeah,
minus
so
three.
if this is the maximum problem, so I just what I do is something. Okay. Okay. Yeah. Sorry. I was just saying that in this case the maximization problem. So you'll just end up getting minus min of minus whatever this is here. Got it?
Yeah.
And only for the optimal value you need to worry slightly. Otherwise you can just directly write it as min of minus of the same thing.
Yeah.
Okay, so only when you are computing the optimal value, when you convert it
Mm-hmm.
into some min problem, then you just add not add but multiply with this minus 1 to get the right sign.
Otherwise, you just change the coefficients of
Yeah.
C, right?
Yeah, otherwise it's straightforward. So
And anyways, the question after that already asks for a formulation of the dual, so you have to do all those things like conversion into standard form and all.
I'm not sure. Let's see. Let's first solve this.
Yeah. So, okay.
Okay, so first things first, we are given our x1 star, x2 star, which is 0, 3. So we know that this is LP, so strong duality holds, right? For this optimal point, you can whatever value you get has to be the same value for the dual for its optimal solution. So let's just first look at the optimal value. What is the optimal value? That's 0, comma 3, just 9, right? 0 plus 3.
Nine.
Uh, so okay, I don't think that will help. I think that this is not help. Yeah, I think what we can do is we
Yeah,
can.
you have to bring out the full equations and solve them simultaneously.
Uh, B is given to me, right? So I can write this. So I'm just writing the optimal value. I'm just equating. I hope this is fine. I'm just equating the optimal values.
Yeah, yeah, that's fine.
Okay, and by complementary slackness. what will I get? So I have y star transpose. So let me write the constants later. First I will okay. So my A here, what is my A? 2111. My B is 53. And my C is 23. Think if we solve this, so think y1 star should come out to be 0 and y2 star should come out to be 3. And should be fine. Well, at least one sanity check can do is if you put this here 5 y1 star plus 3 y2 star, you actually get 9, right? It's the same as 3 times 3 plus 0. Okay. I think it's also easy to see from here, for example. Okay, maybe not this one. 1.8 times 5 is still 9 here, so this doesn't completely eliminate it.
Yeah, but you can
Oh,
narrow down somewhat options maybe.
I mean D definitely goes out 0 0. But I
Yeah.
think A, B, C, in terms of, if I just look at strong duality, I think all of them satisfy 9 optimal value. So here I
Yeah.
think even for C, 5 plus 4, 9. And same for here. Yeah. So okay, maybe at least strong duality helps us eliminate D. It is somewhat obvious because we know that x1 star, x2 star are not 0, so not of much help. So yeah, I'm just skipping this step, but it's pretty much just
Yeah,
two plus
same.
two
It's the
variables.
same as the last problem. Yeah, same.
Uh, so I think you're talking about this question, right? You're saying something about
Yeah,
complementary
means
slackness.
I was saying that we have to formulate the dual in the standard form. I think this is the one.
Yeah, I'm just thinking maybe may not have to, because we are trying to solve these questions without explicitly rewriting primals as duals. So let's say this is the primal and the dual is given by 4y1 plus alpha y2 y1 plus y2 psi beta. Strange looking way of writing things, so we will see what this means. Y1 minus y2, then there is some symbol psi again, and then there's a constant one, so beta is also some constant, psi is some symbol, so I'll explain in a moment. Okay, so alpha beta are integers, so there's a alpha here and there's a beta here. And psi is basically one of these inequalities, greater than equal to, less than equal to, or equal to. The question is, what are the values of alpha, beta and psi? And the options are 2 1 equal to 2 2 greater than equal to 1 2 greater than equal to, and the last option is 2 2 less than equal to.
converting it into slash variables and all those things. Yeah, you can just.
Without that, can we do it?
I think so. Just let's. I have done this by just writing out the A and B matrices, A, B, and C matrices, and just putting it in a dual form.
See, one thing, for example, we already know. If we have a problem, LP problem, which is stated like this, and we know the dual form is stated like this, then we know what the size should be, right?
Yeah, that we can know.
So psi is what?
Psi should be greater than, right?
Yeah, greater than equal to.
Psi should be greater than, yeah.
So that means few options go right away. So only B and C remain. And that also we know. And why is that?
Which one?
So what I'm saying is, uh, for example, do we know something about this beta?
Yeah, we know that, right? It should be greater than equal to C, right?
Yeah. So then that means
So
uh,
it should be two.
2
Beta
and
should
1.
be
So
two.
we know that C is C. Sorry, not C. Beta. Beta is 2, right? So because dual is min y p transpose y, a transpose y greater than equal to c, y greater than equal to 0, primal is max c transpose x, ax less than b, and x greater than equal to 0. Okay. So
Yeah.
well, that doesn't really help us because that was known. That's the same, so it doesn't really. We still have to find the alpha. That anyway we have to find
Yeah.
whether or not we are given options. So what can we do now?
Alpha.
So remember, what is this here? P transpose y, right? So alpha also has to be 2, right?
Yeah, it has to be two.
See, so here we assume that this is given to us. If we did not assume this is given to us, then how do we do it? Same as before, like you said, complementary slackness.
Okay. Dual is not given to us. You are saying that the
Yeah.
form is not given to us,
Yes.
right? Okay.
So I have not tried it using just this. This is my guess. Can you just try it out and let me know? I don't know if I can just use this alone to do it. I suspect
Which
I'll
one?
have to, so if I, although I said this, I don't think using just this complementary slackness equations will be helpful. I'm not sure. I just did it because
I
I know the primal and dual forms. I just proceeded like that. Without knowing the form, I think no. I think one will have
no.
to
I think
already
it.
derive this.
Yeah, it will not be possible.
So then the exercise is how to go from primal to this dual. So just try this out. If you are not able to do, we can try out a few of them either later in the time that we are left with or next week. Okay.
Yeah. Okay.
So maybe 10 more minutes.
I think Yeah, I think anyways we are done for the day nearly, right?
Yeah.
Because so probably it will be a good thing for next week on.
Okay. So we will, let me copy this. We will use the same information that's given here. Right, so we are just given the same setting of question 9 before, and so I think now that we know what these values are, so we can just replace that here. Right, I'm just not missing anything, I think. Oh, beta has to be 2, I think. Yeah. So anyway, this is the problem that we are given, and the question is which of these are optimal solution of primal and dual. So let me write down the options. For primal it is 2 comma 2, for dual it is 1 comma 1, for primal is 3 comma 1, for dual it is 1.5 comma 0.5, for C says primal 4 2, dual to 1, and fourth option says primal is 2 1 and dual is 1.5, and maybe none. So this is the setup we are given.
So do we not need to actually solve this, or can we eyeball the
Yeah,
solutions?
eyeballing. Yeah, we don't need to explicitly solve this. So we are just
We're
checking whether.
eyeballing, right?
Yeah. So what is the first thing that we could check to eliminate some options?
Feasibility, right?
Correct. Feasibility. Yes. So for example, uh, this seems feasible, right?
Yeah, this seems feasible.
Okay. So I'll just write F for feasible. How about this one? 1 comma 1 for the dual.
No.
Mm, okay, because of this, right?
Second condition. Yeah.
Right. So this is infeasible. Okay. How about the second one? So basically, this option A is out of the picture. Okay. How about this 3 comma 1? Seems,
Yeah, that is for primal is feasible. Yeah.
yeah. But dual
Dual.
1.5.5.
Yeah, dual is also feasible.
Then 4 comma 2.
This is feasible.
4 comma 2.
4 2. Oh.
4 plus 2 will not be less than 4, right?
Okay. This is not. This is not.
So this goes. So doesn't matter what the other thing is, it's not
Yeah,
feasible.
but dual is feasible.
Dual
Anyways,
is, yeah, dual is feasible, correct.
and D.
So
This is
two,
feasible. Primal is feasible.
Primal is visible, right? But then
And
this is
dual is
invisible.
not. Dual is not. Yeah. Oh, so you have eliminated all the options. Yeah, this is so simple. I tried solving the things. Oh my god.
No, actually, that is necessary. I mean, here is just because it's options, so um, we can see this. So okay, but does this stop here? Feasibility check. So that does this mean B is the answer?
No, we have to check for the strong duality, right?
Yeah.
Because none of this option is there.
Yeah. So what you have to do is 3 comma 1. We have to put it here. So it is 7, right? 2 into 3 plus 1, 7.
Yeah.
And similarly, this 1.5.5. So this
This
is
is
6 plus 1, 7.
this. Yeah, this is also 7. But if we had to solve this, it would not be possible at this stage, right?
I mean, because here it's a relatively straightforward case, no? You can just geometrically see what's going on. It's just
Yeah,
2
geometry.
R2. So here you can do it. You're right. You can just draw the figure and do it.
But in higher dimensions, analytically, it's not possible with what we have
Yeah.
learned till far, right?
By the way, I think this is what they meant. If you remember, there was a question in last problem sheet.
Yeah.
I think it was
Yeah, yeah.
supposed to be less than equal to 4, not greater than equal to 4.
Okay,
I
okay.
think then it would maybe make sense because here we are getting some non-empty feasible set.
Yeah, yeah. Maybe. There is some slight these things here. Slight oversight there, maybe in the problems.
So need to be slightly careful again. So uh, strong duality holds, and more generally we need to check for complementary slackness.
But here, this is not this. This suffices, right? If we check the strong duality conditions.
Uh,
Because strong duality and these things are equivalent, right? The complementary slackness.
See, the problem is the two values are equal. The
Huh?
strong duality. So I think that's what I think I was trying to avoid that, but I think I was not clear. So okay, so what we checked is just that these candidate points happen to have equal value. We didn't
True.
say that these are optimal for the individual problems and then the value happens to be equal, optimal value. Okay.
Okay. Okay.
So
Okay.
I'm sorry for that sloppiness. So just to avoid confusion, I will remove this. That's not what I really meant to do. That's more like a sanity check at the end of the solution.
Yeah. Those values have to be equal and they have to be the optimal values, right? Then only the complementary slackness condition holds, right?
Yeah, so that's why this condition makes sense to actually satisfy complementary slackness, because we check the feasibility and we are saying that complementary slackness holds. That means there's only one possibility. They are optimal.
Okay. 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 Yeah.
Okay.
Yeah. Okay.
Dual of dual is primal.
Yeah, this is true. This is simple enough.
Uh, right. So this is true. By the way, I hope you are still able to see my screen. No issues.
No issues. Otherwise, I would have told you.
Okay.
Yeah,
Okay.
no problem.
All right. Last question. So today, surprisingly, most time went in these questions. Couldn't
Yeah,
follow.
because that is the right thing to do. First go in the questions and then probably the extra part.
Okay. Also, this is a bit longer than I expected this time.
Yeah, this time I also spent more questions.
So, I mean, just to reiterate, I hope that this point of the importance of complementary slackness is clear. So, we are not just
Yeah,
checking
it's
for feasibility and optimal values being same. We also require the complementary slackness to hold. So, this is a very powerful result that we are going to use again and again to check for optimality.
the complementary slackness part, right?
Yes, yes,
Okay. It's good that you had mentioned this.
yeah. So here, I mean, just to add one more point. So I was saying earlier, right? So optimal values here they are equal because strong duality holds. But in general, like you were saying earlier, that there's a duality gap. So in
Yeah.
general, if I am optimizing over any function, the strong duality need not hold.
Okay. Okay. But complementary slackness will guarantee the optimality, right?
Complementary slackness here, it has to be satisfied. I'm just thinking if this will be a sufficiency for any non-convex. I don't think so. It's just a necessary condition.
Okay. Okay.
So here, just keep in mind that the version that you are seeing here that is specifically for linear programs.
Okay. There is a bit of confusion in regarding that, but nice that you have cleared it up. Yeah, I was a bit of a doubt for that in that. Yeah.
Yeah, I because for example, if you just so this is just an aside. So for complementary slackness, so we were utilizing the fact that the constraint is inequality constraints. They are of the form either this or this, right?
Yeah.
So that's why we were able to write something like,
Yeah. True.
so the form that you have seen about the linear form that won't hold true in general.
Mm.
What you can hope to get is, instead of this, what you can write is g of x less than equal to 0.
Ah. Okay. Okay. Okay.
Okay, so what you'll end up getting is, so instead of this, what you'll end up getting is, so this something like this
Ah.
that you are expecting, you won't get that. Instead, you will replace it by this complicated constraint function.
But G is a vector valued function here,
Yes,
right?
yes.
Ah. Okay. Okay.
So I'm
Okay.
saying
Okay.
that whatever you are seeing, it won't be of that form. It will be a slightly different form.
Yeah, because the objective and the constraints all have changed,
Yeah,
right?
yeah.
Mm. This is-
Okay. So last question, and then we'll stop. So we are given a min cut problem for which we are given a graph. So the point is to move from source to target, and the network looks like this. So here what you are saying about a flow problem, right? Let's say having bidirectional arrows. So I'm
Ye-
allowing that here.
Yeah, yeah. I was asking precisely this thing.
Okay, so Now in general, the thing is finding in general, finding the min cut is not trivial.
Not trivial means intractable
I
or
mean, not easy. Yeah, that's what I.
okay.
Yeah, it's just the English meaning, not easy. Uh,
Okay,
so
okay.
so so here we are given that the optimal cut. So let me recall the definition of cut. So cut is basically all edges ij I in so the graph is basically my collection of vertices and edges, all edges such that I belongs to some set S, which is a subset of the vertex set, and J belongs to S complement. Is that fine?
Yeah.
So for example, if I put a cut here, so see the point of cut is to split the vertex set into two parts, into two disjoint parts.
Yeah, yeah.
So
Yeah.
that's fine, right? So for example, if I put a cut here, that means I am calling this SAC as one set, and I'm calling this BDT as one set. Okay.
Yeah, yeah.
So I'm just separating these two subsets of the vertex set.
So basically the graph gets disconnected into two disjoint parts, right?
No. So we are just separating the vertex sets. I mean, the cut could be complicated also. Cut could be, I could have cut here, could have cut here, could have cut here. Depends. Doesn't have to
Okay.
be continuous, so to speak, like this. I mean, continuous as in I'm saying like a pictorially. If I draw a line like this, doesn't have to be like that.
Okay.
All that I'm saying is, I separate. Let's say this is a set that I want to separate from this set.
Anyways, Deep, your pointer is not visible to me. I don't know for what reason.
Uh,
Yeah, now it's coming. Now it's coming. There is a bandwidth issue, I think.
okay.
I don't know.
Are you able to see
Yeah,
now?
now. Yeah, I'm able to see now. Yeah,
Okay.
previously not.
Yeah. So I'm just trying to say that all in general. For example, here the way I have drawn a cut. Sorry. Here the way I've drawn a cut. It's pictorially it looks like I'm just split cutting through the graph so that it's becoming these two pieces. It's true, but I'm saying I can do it in a very complicated way also. I could pick in this complicated graph a bunch of vertices as that is dependent on the problem that I'm trying to solve, right? For example, I would want to separate S and B from A C D T set.
Okay.
Then that's not like saying I put a cut like this or like this on the graph, right?
Okay, 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 okay.
Okay, so right, so that's why when we say cut, what we mean is we take a set S, we take a complement of the set S, we only take edges which are going from this set S to its complement. We call that as a cut.
Okay, okay.
Okay.
Got it.
Right, so we are given that the optimal cut is produced by the partition S, A, C, D and B, T. So what is the max flow from source S to target T?
Here, optimal cut means the main cut, right?
Yeah. So I mean it will be probably difficult to check, but here we are just given for the sake of illustration that uh, so what we are doing is we are separating this set of vertices from this remaining set SACD. I hope you are able to see my pointer.
Yeah, it's visible now.
Okay, right. Uh, yeah, so basically we split this vertex into these two parts. So what is the maximum flow that can go having cut like this? So how can we cut? Can cut like this, right?
Yeah.
So this is our cut. So what is the maximum flow that can go from source to target?
So you count the number edges along the edges which gets into the cut, right?
So okay. So let me just maybe highlight one more point. So it's not just a mere calculation, but here it's just to throw back to the point mentioned in the lecture. Min cut is the dual of max flow. Therefore, both have same optimal value. Now we can do whatever we are doing. Is it fine?
Okay. Okay. This way we can connect the two, right?
Yeah. So now it's a simple problem. We go from S to T maximum flow. How can we do that?
So you just exhibit the cut on the graph and see what it cuts to the edges. And I did it like that, but I don't know if there's any other way.
Yeah. So okay. So what should be the cut? So we know that this part is to be separated from this part, right?
Yeah.
So how would I do that? So which edges would I want to cut?
H12 on the top.
Right.
So
Then
it's better if you can demarcate on the so that
yeah.
not
So
be
I'll just use maybe red. So yeah, we can cut this. Okay.
uh, and D and T, right? So you cut through 4 at the bottom right.
Yeah.
Then D and T you want to disconnect. Okay, then you cut through 7.
I cut through 7. Yeah.
D and T. And I'm not sure about the 9 because it's pointing in a different direction, right?
Yes.
So that will not be included, right?
Yeah, we don't need to worry about it. You are right.
Yeah. So it's some of those 3 numbers.
Yeah. So cut A to B, D to B, and T to T. B to C is going out from B to C. Okay.
So we need not subtract also that figure. It's just not in the set.
Yeah, so not included in the cut.
Yeah, it's not in the set. Yeah.
Okay, so cost of mean cut equals to cost of max flow equals to 12 plus 7 plus 4 equals to 23.
Yeah.
Okay, so maybe I'll just stop the recording. Give me a second.
Yeah, sure.